Welcome back on a Free Just Friday. We're going to talk about the polarity of molecules. If you watched the last three videos about VSEPR drawing, now we're going to talk about if molecules are polar. So we've got several examples up here. All of these VSEPR structures you've already done, again, if you've looked at the previous videos. Here we're going to start with nitrogen trichloride. Nitrogen trichloride is a polar molecule. And it is polar because it's non-symmetrical. Again, you have to visualize this stuff in your mind. If this lone pair is coming off the nitrogen, and if we start manipulating in our mind, there's a plane of symmetry between these two chlorines, a plane of symmetry between these two, and a plane of symmetry between the back two. When we view it like that, it is symmetrical. But as soon as you start viewing it with a different plane of symmetry, like between this chlorine and this chlorine, then you start to begin to see that it's asymmetrical. So this is nonpolar. Carbon disulfide. Carbon disulfide is nonpolar, and this is because it is a symmetric molecule. The electrons aren't getting pulled in any particular direction. Sulfur is not a particularly strong electronegative element, nor is carbon, so the electrons stay centered between these two bonds. It is nonpolar. Now this next one people get upset about, but when we start talking about polyatomic ions, the nitrate ion, we are not going to talk about the polarity of ions. This is just an ion, we're done, not going to talk about polarity. Phosphorus pentachloride. Phosphorus pentachloride is nonpolar. All the electrons are getting pulled equally in all directions. And when you have something like that, that defines a nonpolar compound. All right, next up we have methanol, and you can see we got this guy out here. One very good indication if something is polar is to see if it has what I'm going to call half of a water. Water is H2O. This alcohol group is an H and an O. This is a polar molecule because all the electrons are being drawn towards the oxygen, giving it polarity, so this is our polar molecule. This is ethanol. We have our two carbons, this is ethanol. Again, we have our oxygen out here, we have what looks like half water. This is where you have to have a little bit of finesse, all right? A lot of you play sports, okay? If you talk about doing something in sports, some sort of athletic movement, you can give a verbal definition, but that doesn't mean you can do it well. There's a gray area. All right, if I'm catching a pass, I can catch it in a certain way, but if it hits me in the stomach first and then kind of bobbles around, it's not a very good catch. I still caught it though, right? Well, here we have to start looking at degrees of how polar something is, all right? Ethanol is not as polar as methanol because this oxygen isn't really affecting this carbon. It is, however, still a polar molecule. Here we run into something interesting. All right, here's our hexagon with our two alcohol groups, except those two alcohol groups can be written in different spots. Here they're opposite of each other. All right, now we have two half waters here, so this is actually a polar molecule. Here they start to bend a little closer together. This is a polar molecule, and this is a polar molecule. You can see there are three different ways of writing the same compound. Now we get to our acids, and the beauty of acids are that if they dissolve in water, they're going to be polar. Here, phosphorus is in the middle. The electrons are getting pulled towards all the oxygens out here. However, because these hydrogens are attached to those oxygens, electrons are getting pulled this direction as well. And what we end up with, net overall wise, is an area of negative and positive. This is polar. And I'm just going to write them down because these are all polar because they all dissolve in water. So hopefully this helps. These are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 compounds that we did in the other videos. All right. Polarity can be a little bit confusing. Hopefully this gives you a little bit of insight. Just remember, if something is symmetrical, it is nonpolar. If it is asymmetrical, it is polar. All right, and the reason for that is we get regions where electrons are and regions where they've been pulled from. And in doing so, you get an area of negative and an area of positive. That means we've created, in essence, a very small bar magnet. So here are 10 examples. And hopefully this enlightens you on how we determine polarity.